I'm audible, right?
Yes, sir.
Okay. Sorry for the network issue. Now I think it should go fine. Um, Let me just
Yes,
share.
sir. It's fine.
Okay. You asked about the Calais theorem, right?
Yes, sir.
Let me just open that note and share the screen. It's visible, right?
Yes, sir.
Okay. So let's discuss from beginning itself. So what Cayley's theorem says, it says that every finite group can be embedded inside a symmetric group of uh, on n symbols, where n is same as the uh, order of the group. So uh, to embed it inside Sn, we need to define certain action, and since we want to embed it inside Sn, which is just a group of bijections on n symbols, which we have to realize each element as a bijection. So for that, what we do, we first look at this left multiplication action on G, which is sending the tuple G comma S to the product GS, and then we look at the function phi g, which is defined from G to G. So just keep one thing in mind, that what is the goal? So goal is to see each element as a function on n many symbols, and where n is same as the order of G. So now we are trying to see each element as a bijection from G to G, right? Makes sense?
Yes, sir.
Okay, so for each small g, we are defining the function phi of g from G to G, sending the element small s to the product gs. So in this way, it is just permuting the element of s, permuting the element of g by sending small s to the product small g time s, right? Now, one need to check that it is a bijection. So Uh, first of all, it has to be well defined. What we mean by well defined, that if two elements are different, if S1 is not same as S2, then phi g of S1 should not be same as phi g of S2, which you can see easily, right? So if S1, S2 are uh, different, since G is fixed, G of X1 and G of S2 will also be different, right? And now this is well defined. We need to check that whether phi j is 1, 1 and all on 2. So for that, we first start with the phi g of S1, phi g of S2. Means if the image is same, whether the element we started with are different or not. So this will give g of S1 equal to g of S2, and we can left multiply it by G inverse, and then we will get S1 is same as S2. So it's 1, 1, and it is on 2 as well, because given any S in G, uh, we can look at the image of G inverse S, which will be mapped to S again. So this is 1, 1 and on 2. So it's a bijection. Now, since it's a bijection and the number of elements in G is N, so it's a group of bijections on a set with N elements. The numbering can change. In SN, we take bijection on 1 to n, but here we are taking a bijection on the set G, which has elements say G1, G2, and Gn. So that's what they are doing here. That SN can be identified with the group of bijections of G. And that's it. It's just an identification with so sending the G to Sn, which is by just mapping small g to the bijection phi of g. So in Sn, we look at the permutations of the symbol 1 to n, but instead of looking at the permutation of the symbol 1 to n, we are just looking at in permutations on the symbols of which are just denoted by group elements. So group elements, like if they are just G1, G2, and so on, the numbering should end at order of G many times. So the last one should be Gn, where n is the order of G. So it's just a reinterpretation of Sn, and that's it. That's what they are saying here. You can map each element small g to phi of g, where phi g is a bijection. So phi g belongs to Sn. And it's a group homomorphism that is easy to see because these are two functions and from G to G. So they will be and how these functions are defined. So this will map S to G to S, and this will map again G to S to G1, G to S. That is what this function is doing. This will directly map small s to G1, G2, S. This is homomorphism as well. And since I think that's it. That's what they are showing here. That phi of G1, G2, S is same as phi G1 and phi G2 of S. Phi is a group homomorphism that we have already seen. And I think that should be right. Now they are telling more about the kernel. So what is the kernel here? So if some element belongs to kernel of this capital phi, then phi of g, that is phi uh, subscript g, should be the identity permutation, right? Because what is the identity element in Sn? That is just the identity permutation, which fixes everything. So that is what they are saying ahead, that it should be the identity element of Sn, and thus it should map everything to S. That means GS is equal to S for all S belongs to S. But if you post multiply it by S inverse, that will imply G's identity. So the only element inside the kernel is the identity of capital G. Thus, this map phi is 1, 1. Clear? So we first showed that there is a map from G to Sn. Then we proved its homomorphism part. And now we have established its 1, 1 part, right? Till now, it's clear.
Yes, sir. So,
So if there is any doubt, you can ask me. Otherwise, we will proceed.
mm, so again, so the initial statements were sufficient, right, to show first uh, they define the homomorphism, then they show that uh, it's one to one and it's on two, and
So,
then showing it's a homomorphism. That's sufficient, right? I don't understand
uh
why the
so,
extra steps are there.
so see, that just told you that. So what we have lost if we don't show the kernel is trivial. That is what you want to ask.
Yes, sir.
So if the kernel is non-trivial, then what would have happened? Then by first theorem of isomorphism, G modulo that kernel would be isomorphic to the image, right? Which is a subgroup of Sn. So some factor group of G is isomorphic to image, not the entire G. Okay,
Oh, okay, sir. Yes, sir.
but we want the entire G to be some subgroup. Okay. That's why the kernel part is, see, telling that everything is a permutation is not good enough to say that that set will form a subgroup, right? It may just be a subset. We just showed that each element of G is realizable as a permutation in Sn. We have not shown that that uh, it it is same as some subgroup of Sn. Two elements may coincide to give one element in Sn, right? And the resultant uh, image may not be a subgroup. So, to make sense of that, we showed that the kernel is trivial. Now, by the first theorem of isomorphism, uh, G is isomorph G modulo the kernel, which is just G because the kernel is trivial, is isomorphic to the image of phi. And for a homomorphism phi, the image is a subgroup, which proves that G is a subgroup of Sn. Fine. Any doubt in that?
No, sir. Now it's okay.
Okay, so this completes the proof of Galley's theorem. Okay, so if you have any other doubt, you can ask. Otherwise, we will start discussing assignment one.
No doubts, sir.
Okay, we just begin with the assignment part. With this. Let me just take the question. Okay, you can see the question, right?
Mm. Sir, I think this is from a different assignment.
Also, feel like maybe some other assignment I don't know. Yes, yes, it's very first assignment. Showing I have not submitted the assignment. Yes, you can see the question now. So we need to choose all the correct statements. We just remove this part. This is my mistake. Okay. If we know the class equation of G, then we can determine if G is abelian or not. What do you think? Is it okay to say that?
Yes, sir.
Why is it so?
So if I take the um, conjugacy classes, then I'll just get 1 plus 1 n times. So based on the equation, I can tell if it's abelian or not.
So I'm writing one statement. You just tell me whether it's correct or not. All terms, or let order of G is M1, M2, and so on, MR, be the class equation. of G, then G is abelian if and only if all mi is equal to 1, right? Is it correct?
Yes, sir.
And this is because um, class of X is equal to X for all X belongs to G if and only uh, or maybe a slightly better version of it. Maybe that will help us in solving other parts as well. This is for some X belongs to G if and only if your X is inside the center of G, right? So if you want everything to be singleton, the entire root has to be the center, and thus the root has to be abelian, right?
Yes.
Okay. What about the second part? If the class equation is this, the center of G has four elements. Is it true?
No, there
Why?
should be so there should be four terms which are one, but here there are only two of them.
So this only implies that, right?
Yes.
From the above observation, this observation, we conclude that the number of ones in the class equation of G is same as the order of the center, right? So since 8 is equal to 1 plus 1 plus 2 plus 2 plus 2 has only two ones, therefore the order of the center is 2, not equal to 4. Now, can this be a class equation? First of all, this relation cannot be a class equation. Can anyone tell me why?
Because the sum should be equal to the order.
Here the sum is equal to 8. 1 plus 2, 1 plus 3 times 2. That is 8 only, na?
Yes.
Okay, we will see it in the later questions. Now, what about the third part? Can G be a group of order 24? If the class equation of G is 24, is this, then G is not cyclic. Is it correct?
Yes.
Why?
Again, statement one implies that this group is not abelian. which implies that it's not cyclical.
Very good. So from part one, G is not abelian. Which implies definitely G is not cyclic. Okay. Now, what about the fourth one? If we know the class equation of a group G, can we determine if G is cyclic or not?
No.
No. Right?
So, okay, so for
Which
example,
is
if I take the Klein group and the cyclic group of order 4, they both give exactly the same class equation, but then one's cyclic, one's not. So this
very
alone
good.
is not sufficient.
So for example, the class equations of A4 and Z4 are same as 4 to be 1 plus 1 plus 1 plus 1, something right. The class equations of these groups are same, but A4 is not cyclic and Z4 is cyclic. So they have the same class equation, but one is cyclic, other is not. Okay. So we can only determine at max the abelian or non-abelian nature, but we cannot say about whether something is uh, cyclic or not just by looking at its classification. Okay, good. So now let us move to the next question. Which of these is the class equations for a group of the appropriate order? So now we need to tell in which cases the expression cannot be a class equation. So before going to that, let me uh, tell you some properties of class equations. So solution two, if bond C with M1, M2, so into MR is the class equation of G of some group G. This is a claim which we will prove. So first part is MIs should divide order of G for all I belongs to 1 to R, right? And second thing is R should also divide Instead of should, I can simply write divides. So can anyone tell me why?
Mm. So the orbit step due to the orbit stabilizer theorem.
Right, right.
So
So
the
what is the explanation?
the conjugate order of um, the conjugacy class.
And there is one more
That's
property. Let me just write that also. It says that number of ones in the equation must divide must be greater than one, greater than or equal to one. Or maybe I can write it in a better way. The property says size of the set mi such that uh, mi equal to 1 should be greater than 1, and this set, this size divides the order of 3. The third one is the most easiest part. We have already explained it. Okay, you can start answering from whatever part you want. What is the explanation for what?
so when I so again for some mi, no,
Some mi.
sir, am I audible?
Right, right. You're audible. Please proceed.
So the order of G divided by the centralizer of element G will give me the order of conjugacy class of G.
So for
And
any,
I know
uh,
that the centralizer of G is a subgroup of G, which means it divides its order divides the order of G, which means even the
uh,
order of the class should also divide G.
okay, very good. So for any G belongs to G, class of G is same as um, G modulo centralizer of G, right? This is what the notation centralizer of G in capital G, right? And this implies, is it okay, right?
Yes.
This contain all the elements which permutes with G. But why it will be normal subgroup?
Will be abelian.
It will be abelian. The, the group is not abelian, right? So we need to check why G at G inverse uh, fixes. Uh, since we are starting with G, we need to show that H inverse K H of G is same as G. Why is it so? You have an explanation for that. Yes.
Sir, you're not clearly audible.
Now am I audible?
Uh, yes, sir.
Why is it normal? Uh,
Um, Sir, your voice is a bit faint.
is it okay now? Hello?
Yes, sir. It's okay now.
I was just connecting my charger. I was connected. So yes, I was asking that why this should be the G again. So
Sir, for the centralizer,
yeah, but so you want to say that centralizer is always normal, is it?
yes, sir.
But I'm just asking the proof that it should be proved in this way, right?
Oh, but a centralizer is always abelian.
See, if it is abelian, that doesn't imply that it's normal.
Oh,
Subgroups of abelian group is normal, but uh, if a subgroup is abelian, that doesn't imply that it's normal, right?
oh,
For example, in Sn, any subgroup generated by an element is abelian, it's cyclic, but Sn just have one uh, normal subgroup just that is just An, right?
yes, sir.
Being abelian subgroup doesn't imply that the subgroup is not abelian. So in general, the subcentralizer of an element may not be a normal subgroup of G. Okay, do you agree with that?
Yes, sir.
You just go and check. So it is a subgroup, but it may not be a normal subgroup. Now, if it is not normal subgroup, can we still talk about G modulo centralizer?
No.
The answer is yes. We normality only guarantees that uh, it will be a group, but we can still talk about the cosets, right? So this just implies that this is cosets. So it's a caution. It may not be a group. And it's a group if and only the centralizer is a normal subgroup. But we don't need anything specific from the group property of this set. We can still talk about the cosets, right? We can talk about the set of all left cosets of it, and class of G is just a set of left cosets. You can even see this from here. So conjugacy class of of an element is it a group? It's a group if and only if uh, uh, its identity, right? That's the only case because identity forms a singleton set as conjugacy class, and no other conjugacy class contains identity. So, except identity, no, there is no possibility of having the conjugacy class to be a group, right? I think I should just note it by C of C. So you got my point?
Yes, sir.
So conjugacy class of an element is a group if and only if that element is trivial or the conjugacy class is trivial. In all other cases, the conjugacy class does not contain the identity element, and thus this will not be a group because uh, if this is not a group, then definitely this is not a group, and that implies that the subgroup with whom you are modulo it, with whom you are factoring it, that is not a normal subgroup. So the centralizer of G is never a normal subgroup except for the case when G is trivial. Okay, this is the identity element. But we can still talk about the number of left and right cosets. And here it is just the number of left cosets. Okay, you got the point?
Yes, sir.
Oh, fine. So, so size of conjugacy class of G is order of G modulo uh, the centralizer of small g in G, and thus this implies um, class of order of class of G, which is of course integer or a natural number B. So this implies that the class of G divides order of G, and which implies the first one is true. Mi divides order of G for all I belongs to 1 to R. Now, what is the explanation for the second part? That number of conjugacy classes divides the order of G.
Well, he was not audible.
Huh? whether it divides or not.
Mm. Sorry, sir. Till till now you are not audible.
Am
I
I audible
thought,
now?
but now you are audible.
So I'm saying a number of conjugacy classes divides the order of G. Is it a correct statement?
Yes, sir.
Then how to prove that? So this is in fact not a correct statement in general. Can you give me a counter example? Am I audible now? Hello?
Yes, sir.
So I don't know it's from your side or from my side, the connection. Are others uh, can hear me or not? Am I audible to others? No response.
Yes,
So I
sir, you are
just
audible. Yes, sir, you are
okay.
audible.
Okay. Thank you. Thank you. So yeah. So I'm saying it's not a correct statement. Can you tell me some counter example? I just wrote it to check you whether he was following or not. So number of conjugacy classes won't always divide order of three. And you all know the example. What is the class equation of Q8? Quaternion group. Instead of claim, I am right. I will write it like that. Then check the following statements. Thanks. I have made one more mistake. I should not write 1, 2, and 3. They are already been used. So I will write it A, B, and C. You guys till then think of the counter example. I have already told you, try to look at the quaternion group. What is the class equation of the quaternion group? B part A is not true in general. Counter example is the class equation of Q8. And here we have, so there are two elements in the center. We have 1 plus 1. And for I, J, and K, we have two elements in their conjugacy classes. So see, what will be this element? So Ji is minus K and J inverse is minus J, right? This is Kj, which is minus of I. And similarly, if you conjugate by K, you will get the same. If you conjugate by minus J, you will again get the same. You will conjugate by minus K, you will get again the same. And conjugating by central elements will give you I, and conjugating by I or minus I, it will give you I. So uh, the conjugacy class of I is just I and minus I. So this is because, and here you can see number of conjugacy classes is 5, which is not dividing 8. This is because set of conjugacy classes of Q8 is just the trivial one, the minus I and minus I, then you have J and minus J, and then K and minus K, right? And this implies the number of conjugacy classes of Q8 does not divide the size of Q8, right? So the second claim is not true. So you should keep these things also in mind. This is a very common way of getting confused, that whether the number of elements in the number of terms in a class equation divides the order of G or not. Okay. Now let's come back to the third part. Uh, so what is this? Uh, this is just the center of G. Since this set Mi such that Mi equal to 1 is equal to center of G, and we know that the size of center is greater than 1, and size of the center divides the order of G. Therefore, C is true. Okay, clear? Now, can we come back to our question, starting question? So, first one is false. Since 5 does not divide 18, therefore, it cannot be a class equation. And how many ones are there? 10, right? So everything is abelian. So everything is having a singleton set, singleton conjugacy class. So this can be a possibility. So this is not correct, but this is correct. Uh, it is a class equation for an abelian group of order 10. Right? Now, what about the third part? You have seen this class equation before? I'm audible, right? Hello?
Yes, sir, you were audible, but it seems that I have some network issues. So
Okay, okay.
for me, it's
Fine.
on and off, which is why I'm not replying for any of them.
Okay, okay. But you can reply, no problem. So now, this is a class equation for which group? Class equation for S3, right?
Mm.
There is an identity element. There are two 3 cycles which forms a conjugacy class. There are 3 2 cycles which form a conjugacy class, right? What about the fourth one?
Not a possibility.
Not a
Since
possibility.
it
Why?
has to be abelian.
Since all groups of order 4 are abelian, are abelian, this it cannot be a class equation. Okay, good. Let's move to the next part. G be a group of order 112 and S be a finite set on which Gx, order of S denote the order of, sorry, this symbol denote the order of S, which of the following are true statements? First one is saying S is a order of S must be even. Is it true? So let me give you an example. So, trivial action. What it is? For any group G and any set S, we can define a trivial action as follows. As follows. Simply as, so from G cross G, Oh, sorry, not from G cross G, it should be from G cross S to S again. What should be the map? So G comma S is mapped to S again. So G is doing nothing to the element of S. So just acting trivially, fixing each G is fixing each element. So definitely the first property holds. Identity fixes everything because there everything is fixing, and the compatibility condition, the second property also holds because everything is if G1, G2 are two elements, then uh, G1, G2 of S will also fix this S, and if you add first G2 and then G1, then also you will get the small element S again. So it's an action, and this is known as the trivial action, right? Now, first one is saying if the order of G is by 112 and S is a finite set only Gx, then the order of S is even. So first is false, and the counter example is if trivial action of G on any normal on any set of odd order, right? Now, what about the second one? Let S belongs to S. The order of the orbit of S divide 112. Is it true? Yes. Any guesswork? No guess what you want to make? I think we have already seen enough to conclude that. So what does orbit stabilizer product says? Can we conclude anything from there? No comments? So by orbit stabilizer theorem, what we get? Let small s belongs to capital S and An orbit stabilizer theorem says order of G is same as size of orbit of S multiplied by size of the stabilizer of S, right? Which implies size of orbit of S divides order of G. But here the order of G is 112. So orbit of S will divide order of G, and hence this is true, right? What about the third one? This is not true. Can you tell me counter example? We have seen one such. No. So counter example is you can take G as load to be U8 and action is by conjugation. We have already seen that in this case, the number of elements in the class equation won't divide, and this is something else. This won't work as a counter example, perhaps. There, what we were doing, we were saying the number of orbits does not divide order of G, but here it says more. Then the order of the orbit S divides S or not. S and G are both same, then that means just order of G. So this won't be a counter example. So can you give me some counter example? Just try to say something if you are able to hear me. At least I should get some response that will let me know whether you are getting something or not. No matter if it is correct or not, we will see. Even the incorrect statements can lead to a correct proof. Say something that will be beneficial for you also. Brenda, can you hear now? Yeah. Sometimes it raises the doubt that whether I am audible or not. At least write in the chat that whether I am audible. So, uh,
Yes, sir, you are audible.
okay,
I,
thank you.
I think so. It is correct, sir.
This is correct.
Yes, sir.
So, how to prove it? So, what if we take the action of Sn, the permutation in n symbols, on the set 1 to n, right? Sn act on the symbols 1 to n, right? then what will be the orbits? Orbits will be just the size of conjugacy classes, right? So will the size of conjugacy class divide the number n each time? Let me tell you the size counter example. Thanks, Tel, for your response. Let us now produce a counter example. So Sn acts on the set 1, 2 and S. What is the so this is the set, and it should be a map from G cross X to X again. So how we can define this map? So there is a it's here we have some permutation. So let me just write it Sn only. We have some permutation sigma, some index I, and that will be mapped to sigma of I, right? It- It's a action Y, because if we take the identity permutation, it fixes everything, right? And if we take two permutations, sigma 1 and sigma 2, then sigma 1, sigma 2 I, same as sigma 1 of sigma 2 I, right? So the second compatibility equation also holds, and thus it's a action. Now, uh, here for n equal to 3 itself, the result doesn't flow. See here, um, they are telling G acting on a set S, right? So our G is not of order 112, but still we can produce examples where this won't be true, right? But let us first produce the example. So for n equal to 3, let S is 1, 2, 3, and G is S3, then and the action is by conjugation. Then what will be the orbit of 1, 2? Then orbit of the element 1, 2 is all 2 cycles, right? And definitely the size of this orbit is 3. Oh, sorry. I should have taken orbit of 1, 3, 2. That has 2 elements, 1, 3, 2 or 1, 2, 3. You can take anything. They will have the same orbit. So their orbit size is 2. There is some disturbance. So there just there is some disturbance. So Let's just wait. No, it should be fine. So their orbit size is 2, but the s- size of S is 3, right? So here the size of the orbit is not dividing the size of S. Clear? Right? But the problem here is uh, the group has order 6. It's not having order 112. But you can definitely get examples where uh, the size of the orbit won't be dividing the size of the entire set S. We cannot take the trivial action example because in this case, the orbits are of singleton sets. So they will definitely, their size will definitely divide the size of S. But so here is an exercise. Try to find an example when order of G is 112. Okay, so I gave you one example in which orbit number of in which the size of orbit is not dividing S, right? Now you can think of some other example and uh, see that this won't be true. Okay. What about the fourth one? Fourth one is directly true, right? This is just uh, because true because orbits partition gives a partition of S, right? So uh, whatever action you have, whatever set you have, whatever group you have, the distinct orbits always partition the set as. So their orders will be same as the order of S, right? I hope that is clear. If there is any doubt, please
Yes.
ask me. Okay, okay. So we can move to the next part now. So we need to choose all the correct statements. Q here denote the group of rational numbers. First is there is no transitive action of Q on itself. You know what is transitive action, right?
Yes, sir.
What it is?
So there are two elements, uh, G1 and G2, belong to some group. Then I can always find another element so that uh, G1 times some H equals G2.
So Transitive action has nothing to do with that. Means this is a particular kind of action that you are mentioning. But transitive action only means that the number of orbits is one. So given a group G, given a set capital X, G is acting on X, then the action is said to be transitive if the number of orbits with respect to that action is one. So there is singleton orbit. So whatever you were saying, let me just use that language to tell you the definition of transitive action. So given any small x in the set capital X, there exists a group element G. So you can start with any two elements, x1 and x2 in the capital X. There exists group element G such that using that group element, you can map x1 to x2, right? So there is no need that we start within the same group. We just need to start in the set X on which G is starting, on which G is acting, right? Do you understand the difference?
Hmm. No, sir.
So you said that we have two elements G1 and G2 inside G, and there exists some H such that uh, H of G1 is G2, right? This is what you said.
Yes, sir.
Now, this is a particular kind of action for which we know the transitivity. Transitivity in general mean, so an action G cross X to X is said to be transitive if the number of orbits is number of orbits with respect to this action is one. There is a single orbit. So this is whatever you said is a particular case when the action is through left multiplication. So that what you said implies that the left multiplication action is transitive. But this may not be true, but this is not the general definition. General definition can be for any set X and for any action. Okay. For
Okay, sir.
example, the above in our one of the example, this. So Sn acts on the set 1 to n. This action is also transitive because you can map anything to some other index using some permutation. We start with permutation I, you can map it to permutation j through the permutation ij, right? Ij maps I to j, right? So you start with any two indices, there is a permutation which map the first index to the second index. So this action is also transitive. Here, even the set we started with is not a group, it's just a set. That is the definition of transitive actions. Now, what we are supposed to do here, we need to see that whether there is a transitive action of Q on Q or not. So now, can you tell me one transitive action? So you have already given the answer, the left multiplication action multiplication action and Q on itself is a transitive action. And if this is transitive for any group, Q has nothing to do here. So for any group G, there exists at least one transitive action given by the left multiplication on itself. So this statement is false. And as I said, Q is doing nothing here. This can be asked for any group, and for any group, there is at least one transitive action. Second one, let S be the set of divisors of 100. There is an action of Q on S such that R dot tan is 20. Is it true or false? First of all, we need to see that.
Sir, are you discussing the second one?
Yes, the second one.
Oh, uh, the second one is false.
Yes.
But then,
Oh,
since I got the definition itself wrong, somehow I still ended up with the uh, knowing that this is false, but
no, no, but
I don't
this
have
this
a
doesn't
disproof.
this doesn't need to do anything with the transitive action. That's nothing to do, right? I'm just saying, is there a action of Q on S which maps 10 to 20?
Uh, Sir, at least by trial and error, couldn't find any such action, but not sure of a disproof.
Just think for some time if you can produce some counter example. Otherwise, I will give you. Or it may be true as well. So one of them should be wrong, right? It says the stabilizer of any element of S is all Q. And the second one is, and this says that the 10 maps to 20. So if the stabilizer is whole Q, then this cannot happen. And this there are just one element, then the stabilizer cannot be whole Q, right? So one of them should be wrong. You get at least this, but one of them should be wrong, right? They are just contradicting uh, statement. Yes. Shall I leave it to you guys to solve, or you want to uh, state something? So I have already told you that one of the option B and C is not true. Either the stabilizer of any element can be on role of S, or there exists an element which maps 10 to 20. And of course, this is not true, then this is true. We are just left with second or third. So you are having a finite set, right? Now, uh, if Q is acting on that finite set, then what kind of properties it should satisfy? The stabilizer of an element um, must divide the uh, order of G, that is, so here, of course, this is not finite, but for any S, we can still talk about uh, Q modulo the stabilizer of S in this. This will be the same as orbit of the element S. And stabilizer is always a subgroup. So what are the possibilities for subgroups of Q? Any idea? We try to see that if you look at all possibilities of uh, subgroups of Q, then in any case, the quotient cannot be a finite set. Okay, so this might be a little bit involving. So I'm leaving this as a as of now. But the hint is You try to see the possibilities of subgroups of Q and then look at the quotient Q modulo stabilizer of S. Can in any case it is finite? We will end up realizing no, and thus the only possibility of being it having it finite is just when stabilizer is same as Q. So that is the orbit is singleton set. Okay. So uh, I'm not going into detail of it, but I think I have given enough hint, right? So for any element S, the orbit of S is Q modulo the stabilizer, and stabilizer is always a subgroup of Q. Now try to see what kind of possibilities are there for subgroups of Q and in which cases this modulo thing can take values 100, right? So you will see that it is finite only if this is the whole Q. Okay. Okay. Uh, this part I'm leaving with some hints because this seems to be a bit involving, and I have given you enough hint to just go and revisit. Uh, you just need to check what are possibilities for subgroups of Q, right? And you then you see that can it be in, uh, can it be something whose quotient with the whole group Q will give you some uh, finite set except one. Okay. So this 100 has nothing to do with this. This is just based on realizing what are subgroups of Q. Okay. So let me just move to fifth part. It says choose all the correct statements and let Sn denote the symmetric group on n letters. Sn contains groups of order less than equal to n as subgroups. All such groups are there. Is it true? Hello. Is the first statement true?
Yes, sir. Sir, you are discussing question 5, statement 1, right?
Right, right.
Uh, yes, sir.
Why?
So, if suppose G is some group of order less than or equal to n, then if it
No.
has um,
So let me repeat the question. We are given Sn, the symmetric group of on n letters, and the first part says it contains all groups of order less than equal to n as its subgroups.
so all suppose any symmetric group with n less some number less than n automatically belongs as a subgroup, right?
Right.
Mm.
So this is an application of Paley's theorem, right?
Yes.
So let G be a group such that order of G is less than equal to n, then can be embedded as a subgroup inside S order of G. Just write it in here. G is isomorphic to a subgroup of S order of G, which is a subgroup of, or I should not write subgroup, S, which can be embedded inside S of F, right? Since order of G is less than equal to 1. This is by Calais theorem. This part is by Calais theorem, and this is in general true because order of G is less than equal to 1. Now, what about the second part? It contains all groups of order less than equal to n factorial as its subgroups.
This is not necessary. This is not true.
For
So,
example,
okay, if I consider S3,
right?
then um, then I know that um, uh, S6 can't be its subgroup. So
Right. And also, so we can say that 4, 5, and 6, they are all less than equal to 3 factorial, which is 6. But S3 has no subgroups of order 4, 5, or 6, right? Correct? Very good. So, what is what you want to say from third part? The action of the additive group Z on the rational numbers given by the additive action and dot Q is n plus Q. This is transitive. Is it true?
this is not true.
Why?
Mm.
Transitive means it has one orbit. So what will be the orbits? So under the action, let's say 5 from Z to Q, Z given by M going to M plus N. The orbits of not I be an action. So then what we can say? The orbit of then orbit of an element M N is just M plus N, such that M belongs to Z for all N belongs to Q, right? What this implies? This implies if R and S are two rational numbers, then R and S are in the same orbit if and only if R minus S is an integer. Because if R and S are in the same orbit, then R is equal to some n times some m times S, which implies R minus S is an integer, and vice versa. If R minus S is an integer, then if you add, let's say R minus S is n, so m dot, uh, so in the converse direction, if R minus S is n, then that will implies R is n plus S, and which is just n acting on S, right? So R belongs to orbit of S. So they belong to the same orbit if and only if their difference is same. But in rational numbers, there are many rationals which do not differ by a integer. For example, 1 by 2 and 1 by 3. Their difference is not an integer. So they won't be in the same orbit. So this implies phi is not transitive. Clear?
Yes, sir.
Okay. What about the fourth one? G be an abelian group. I think transitively on a set S not be some element S. If the stabilizer of S naught is S, then the stabilizer of any other element is also S. So what does this means? That under a transitive action by an abelian group, the stabilizer of all the elements are same. Whatever be the element you be taking, its stabilizer is always the same. Can you tell me why? Or given so so by your trick, definitely this has to be true, right? Because we have just one option correct till now. But you need to give me the explanation also. So let stabilizer of some S naught is H, right? And S belongs to S, be any element. We need to show that stabilizer of small s is also H. That's what the question is asking, right? S naught is H, then the stabilizer of S belongs to S is also H. So let some G belongs to G belongs to stabilizer of first of all, what is the claim? The claim is stabilizer of S is also H. So let some G belongs to stabilizer of S. We need to show that G belongs to H also. And what is H? H is stabilizer of S naught. So then G of S naught we want to see, right? But we can use the transitivity here and how to use the transitivity. And H belongs to, no, I should not write H. And G1 belongs to G, be such that G1 of S is equal to S naught, right? Why this is? This is true because the action is G acts on S transitively, transitively, correct? You agree with me? It's already given, right? Now, since it's transitively, given any S and S naught, there will be a G1 which sends S to S naught, right? Now, this will implies S naught. We need to show that G is inside H, which is stabilizer of S naught. So G should stabilize S naught. So G of S naught, we need to prove that this is S naught again. But S naught is what? This is G1S. So G1S. And we know the group is abelian. So G1S. This is, since G is abelian, right? And now what is G of S? G of S is again S because G belongs to stabilizer of S, right? Since G belongs to stabilizer of X, therefore G1 of G of S has to be S again. And what is G1 of S? This is S now. So G also stabilize S now. So this implies G belongs to stabilizer of S naught, which is H. What in the converse direction? What in the other direction? So let G belongs to stabilizer of S naught, which is same as H. Then we need to show that G also belongs to stabilizer of S. So how can we do that? So G of S same as G of, now if G1 is S is S naught, then S is G1 inverse S naught, right? So S is G1 inverse of S naught, correct? But again, we can use the invertibility thing, sorry, the abelian thing. This is since G is abelian. So we just do this, and this will imply since G is in the stabilizer of S naught, this is same as G1 inverse of S naught, and this is again same as S, right? Because G1 inverse of S naught is S, because S naught is G1 of S, right? So this implies G belongs to stabilizer of S, and hence stabilizer of S is same as stabilizer of S naught, which is H. So if a abelian group is acting transitively on a set S, then all the elements of S have the same stabilizer. Okay. Fine.
Yes, sir.
Okay, great. So let's move to the last question, and probably the question of last question to be discussed in this course. Let S4 denote the symmetric group of four letters. Which of the following are possible sizes of conjugacy classes of S4? Yes.
9 is not possible. It doesn't um it doesn't divide the order.
Very good. So S4 has order 4 factorial, which is 24. Now since 9 does not divide 24, therefore 9 no conjugacy class can have order 9. Good. What about other options? Three, four, or six. So did you use some um, computation or just use this marked any two of your choice?
I just used trial and error. I'm not sure how to think of this.
Okay. So you know how conjugacy classes in SN are uh, factorized? First of all, let me just answer this question and then I will tell you a bonus fact. Check that the set of conjugacy classes of S4 is the following. So we need to partition 24 elements. Identity will come as it is. Now all two cycles will form one conjugacy class. 1, 2, 1, 3, 1, 4. How many two classes and two cycles are there? 4, C2, which is 6, right? 2, 3, 2, 4, and 3, 4. All three cycles will form one class. 1, 2, 3, 1, 3, 2. Should make it a bit larger. Then 2, 3, 4, 4, 3, 2. No, not 4, 3, 2. It should be 2, 4, 3. Then 1, 2, 4, 1, 4, 2. Two more should come, right? Here 4 is not coming, here 1 is not coming, here 3 is not coming. 2 should be missing somewhere. So 1, 3, 4, and 1, 4, 3. Oh, sorry. 1, 3, 4 and 1, 1, 4, 3. Right. This one's a conjugacy class. It has 8 elements, but this one has 6. So we have 15 now. 9 more to go. Then all 4 cycles. 1, 2, 3, 4. 1, 3, 2, 4. 1, 4, 2, 3. Any other elements remaining? What about 1, 2, 4, 3? And 1, 3, 4, 2. Also 1, 4, 3, 2. There are 6. 6 plus 6, 12. And 8, 20. And then 1, 21. 3 more are missing, which are product of two cycles. 1, 2, 3, 4. 1, 3, 2, 4. And then 1, 4, 2, 3, right? This implies order of S4. To write it in terms of conjugacy classes as class equation, and 1 plus E will come from here, 3. Then there are 2 for 6, and there is 8. So 12, 20, 24, right? So this is the class equation, which implies 4 cannot be false. Even you need not to write the class equation, you can just come from here. So 4 cannot be the possibility, 9 is also not the possibility, and 3 and 6 are the possibilities, right? Now, uh, I leave it to you. Check that sigma 1, sigma 1, sigma 2 belongs to Sn for any n. Then sigma 1 is conjugate to sigma 2 in Sn if and only if sigma 1 and sigma 2 have the same cycle decomposition type. Decomposition type. And given, in fact, given sigma 1 and sigma 2, you can also find the conjugating element. So you just check. Okay. Although this has nothing to do with this example, but this is just a bonus thing for you. Thus, the conjugacy classes of Sn are characterized by the cycle type, possible cycle decomposition type. Okay. Again, let me repeat this. So two elements in Sn are conjugate, then sigma 1 is conjugate to sigma 2 in Sn, if and only if they have the same cycle decomposition type. Okay. So here I just did that. So identity is separated. Should write it as identity only. Singleton set is no permutation. Either you should write like this, the identity element, or you write like this. This is this doesn't represent the identity cycle, right? So this is the trivial one. Then this has uh, only 1 2 cycle. This has only 3 cycle. This has only 4 cycle, and this is product of 2 cycles. So they are tetraized like that. So that's how I could do it very fast. Now you can see what is the class equation for S5 and S6. You just need to see what are the possible cycle types and how many elements corresponding to one cycle types are there. Okay. So I think with this, we can stop the session. If you have any doubt, then you can ask.
No specific doubts.
Thank you very much.
Okay. So thank you both. You are here consistently for the entire course. So uh, I appreciate your attendance and
Yes, sir, you, you are given much clarification on this problem, sir. Once again, thank you.
okay. Thanks to you for attending it. Let me now stop recording and then